Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle force, the last and the final epilogue and farewell episode number 29, in which we will part our ways. But before we part our ways, for a curious traveler, here are a few of my ideas on where you can take your basic knowledge and your basic understanding of inversive geometry further. The way I see it, fundamentally, from here onward, you have four choices. First, you can always drop this knowledge on the floor called Turkey and move on with your life. And as a fair warning, you actually may come across this idea or this geometric transformation of inversion of the plane with respect to a circle in your complex analysis course. So that's the choice number one. Choice number two, you can stay within the confines of the plane, be that plane Euclidean or complex. The choice number three, you can bravely step into the 3 space and learn a little bit of something of how inversion of the space works. And the choice number four, you can combine these 2 steps and deepen your knowledge of how the 2 space inversion works and learn how the 3 space inversion works. If you decide to pursue the study of inversive geometry of the plane further, then fundamentally, the way I see it, you have the following 3 choices. For the choice number 1, you can keep the width of your knowledge fixed, but you can increase the depth of your knowledge. For the choice number 2, you can keep the depth of your knowledge fixed, but you can increase its width. And for the third and the final choice, you can actually do both of these 2 things. You can increase the width of your knowledge and you can increase its depth. For example, if you decide to keep the width of your knowledge of inversion of the plane fixed but drill deeper into it, then one thing you can do is, as I mentioned before, along the mandate of Terry Tao of learning and relearning, you can loiter over the problems that we already solved in this course and try to look at these problems from a new angle or add more material to it. For example, I'll give you the coordinate of this problem number 27. In my free book, Inversive Geometry for All, you will find it in the chapter number 21. And in this course, we solved this problem in episode 26 during the practice session number 8. And as a friendly refresher, in the problem we were given a bounding generating circle. In that generating circle, we were given a chord, and into the space between the chord and the bounding generating circle, another smaller circle was inscribed in such a way that it touched the chord at some point, arbitrary point, let's say, and it touched the outer generating circle internally. And we were asked to prove that the points at which the inscribed smaller circle touches the bounding generating circle and the chord, when extended, will hit precisely the midpoint of the complementary arc of the bounding generating circle, or that these 3 points are collinear or sit on one and the same straight line. So here's the thing that we did not prove, and this is what you can try to do again on your own. You can try proving that if the point that sits in the dead middle of the complementary arc in this problem is connected with the bounding points that define the chord of the circle, then the 2 line segments thus formed will have exactly the same length as the tangents that are drawn to the inscribed circle through the midpoint of the complementary arc. For your second choice of staying with the inversion of the plane, you can keep the depth of your knowledge fixed, but you can increase its width, and here you have plenty of options. For example, you can try to solve new problems, the problems that we have never solved in this course, and here is one interesting problem. Given the circle of inversion and its center and the positive power of inversion, construct the image of a point that is located outside of the circle of inversion or inside the circle of inversion using a straight edge only. Recall that in our course we solved all these problems using both Euclidean tools, a compass and a straight edge, but here we have an additional constraint that we cannot use a compass. In other words, we can only use a straight edge in order to construct the image of a given point with positive power under the symmetry in a given circle, assuming of course that the center of the circle is given. So with this constraint, if you will be able to solve this problem on your own, then you are doing very well, because along the way, this way or that way, you will discover a new, and thus you will increase the width of your knowledge. You will discover a new mathematical notion that is known as the polar of a point with respect to a circle. For your second choice of studying the inversion of the real plane, you can do, for example, the following thing. You can learn new terminology, and in this course I did not want to overload this course with too much technical information because this is an introductory course, but you can learn, for example, the notion of involution in mathematics. So what is an involution? An involution in mathematics, in group theoretic terms, or in group theoretic terminology, is any transformation that has the order 2, or f squared is the identity transformation. And in less cryptic terms, it means the following. Let's say we have a certain transformation when applied to a certain material produces a certain output. If we have this relation on the books, then nothing can prevent us applying this relation to itself. In this case, we will obtain the following. F of x will be f of y, and this will produce a certain output, z. In general and in vacuum or a priori, there is no good reason to believe or think or even demand that z in this case will be exactly the same as x, or it will be x. But if it so happened, that is why there is a big if in the definition of involution, if it so happened that the composition of transformations applied to one and the same material produces the original material, then such a transformation is known as involution, or again, in the group theoretic terms, we will say that the square or the order of this transformation is 2, such that when this transformation, for example, is composed with itself, using the composition notation, will be the identity transformation, or will recover the original fixed material that this transformation acted on. So now the question is our transformation that we studied in this course an involution or not? The answer is yes, of course. One and the same inversion of the same plane in the same circle, in the same center, in the same radius, and in the same power, when applied to one and the same point in succession, one after another, or as a composition of inversions, will restore the original. And we already saw that whether we took the original point A that is located outside of the circle of inversion or inside, this simple, let's say, 2 cycle was evident. It was in place. If we take our point A located outside of the circle and apply inversion with positive power in the given center with a given radius, we will produce its inversive image, the point A prime, boom, we have it here. And if we keep all the other parameters the same, again, the same plane, the same circle, the same center, the same radius, the same power, and apply these parameters to this point, to the image of the point A, then what will happen? We will restore the original, we will obtain the original point A, and that is how the application of the given transformation to the fixed material works. In other words, if we apply this, let's say, operator to this relation again, then this is what we will have. Inversion of A, and it will produce precisely the original point A, and that exactly means that inversion of the real plane with respect to a circle, of course, when all the parameters of inversion are fixed, is an involution. Within the confines of the option number 2, still, you can learn even bigger ideas, such as you can take an introduction to the theory of groups, and here you're in good position because right in the same free GitHub repository where I have my free PDF book, Inversive Geometry for All, I have a similar book called Group Theory for All, a very gentle and very accessible introduction, elementary introduction into the theory of groups, and you can start reading this material and start comprehending and learning new things. Why? Well, because the German-born mathematician Felix Klein, who lived between the years of 1849 and 1925, put forward the following modern, as we take it, definition of what geometry is. According to Felix Klein, geometry is a study of sets of invariants, or the properties of geometric figures that do not change or stay invariant, on the corresponding groups of transformations. And you can see, as you can see in the modern definition of geometry, the notion of a group or a certain algebraic structure takes a central stage. Again, you do not have to have a PhD in the theory of groups, so of course if you do, that's great, but the ideas that I lay out in the elementary introduction to the theory of groups in my book are very accessible, and you can put these ideas to a good use. But before I discuss the areas into which you can pour your combined knowledge of the theory of groups and inversive geometry, the definition of geometry given by Felix Klein apparently is so fundamental that in the theory of groups, there exists a special group called the Klein 4 group, sometimes symbolized like so, K4, and that group has many, probably a dozen good manifestations or incarnations, and two popular ones are the following. The group of rigid symmetries of a rectangle that is not a square, because a square has a different group of symmetries, but the group of rigid symmetries of a rectangle that is not a square under the operation of composition, or what that means is that if we perform certain transformations, reflections of this rectangle in its two axes of symmetry and rotation in such a way that this geometric figure is coincided with itself, then we will always get this particular shape, and thus this is a group. The other manifestation of the Klein 4 group is relevant to computer scientists. Some members of our audience who may be programmers 9 to 5 may or may not know, but our favorite set of 4 strings, binary strings of length 2, 0, 0, 0, 1, 1, 0, 1, 1, under the operation XOR form a group, and that group exactly is of type 4 group or Klein 4 group. Here the identity element is the string 0, 0. The operation XOR is associative, it is binary. This set under this operation is closed. No matter which two elements of this set we feed into the XOR operation, this operation will always pump out one of these elements. Thus, boom, we have a group. Now, when you take this knowledge and combine it, even a little bit of the knowledge, again, you do not have to go way too deep into the theory of groups, but if you spend, I don't know, let's say 2 or 3 months reading through the material in my book, you will be already well equipped with everything that you need in order to succeed in your next step. For example, combining these very basic rudimentary or elementary ideas from the theory of groups with what you already know about inversive geometry, you can take this or pour this into what we can call aesthetic geometry. What is an aesthetic geometry? An aesthetic geometry is the study of algorithms that combine the theory of groups, the material from the theory of groups, with various transformations in order to produce aesthetically pleasing 2-space and 3-space figures. And to give you a taste for what this aesthetically pleasing 2 or 3-space figures may look like, here is what may be called as a harmonic Riemann windmill. And here the name Riemann windmill or a harmonic Riemann windmill may seem arbitrary, but I think that it will emerge naturally once you start working with these things, and you can give it different names. A mathematical necklace, a mathematical bracelet, and so on. And here your imagination is the only limit. You can also drill deeper into inversion of the plane with the specific application of what you already know. For example, you can learn the introduction to the theory of pencils of circles, and here in the lightning round you will learn the following things. You will learn that a pencil of circles is a set of all circles that are orthogonal to two given fixed coplanar circles. These are called the generating circles, let's say C1 and C2. And it is interesting that because two fixed coplanar circles in any given plane can have at most 2 points in common. That means that they can have in general 0 points in common, 1 point in common, and 2 points in common. These are the three choices, and based on these three choices, which are in some sense fixed or defined by the number of possible common points between any two fixed coplanar circles, the three so-called primitive pencils of circles emerged naturally, and the mathematicians gave them the following names: an elliptic pencil of circles, a parabolic pencil of circles, and a hyperbolic pencil of circles. And the definition over here is the following: if two generating circles, C12, coplanar, fixed, and all that good stuff, have precisely 0 points in common, then the corresponding pencil of circles is called elliptic. If the generating circles have precisely 1 point in common, then they're called parabolic. And if these two generating circles have 2 points in common, then the underlying pencil of circles is called hyperbolic. So how does that work? Well, all these pencils of circles are basically partitioned into two distinct types. A primitive pencil of circles of the corresponding type, primitive. The primitive pencils of circles are shown on the top. And the general or non-primitive pencils of circles, these are shown on the bottom, and the idea here is the following. The structure of the primitive elliptic pencils of circles is the following. Such a primitive elliptic pencil of circles is generated by two concentric circles, C12. They have precisely 0 points in common. And in this primitive elliptic pencil of circles, all the circles are actually the straight lines that pass through the center of the concentric generating circles. Remember that topologically we proved that straight lines and circles are equivalent in a specific sense, and you already know what that sense is. So here, when we start dealing with pencils of circles, we also consider straight lines along with circles, or we take that a circle is a generalized straight line. So in some literature you will see circline or circlines when the circle and the line merged into one. So here the generating circles have precisely 0 points in common, concentric, and the structure of the elliptic pencil of circles is all the straight lines that pass through that center, common center of the generating concentric circles. Now, when the two generating circles have precisely 1 point in common, then these two generating circles look like parallel straight lines. So C1 is parallel to C2. What is their common point? The point at infinity. The point at infinity is their common one, these two straight lines. Consequently, the primitive parabolic pencil of circles has the following structure. It is all the straight lines that are parallel amongst themselves and are orthogonal or perpendicular to the generating circles C1, C2. And lastly, if the two generating circles have precisely 2 points in common, then the corresponding primitive pencil of circles is called hyperbolic. So what are the 2 points in common over here between the generating circles? Well, in this case, the generating circles look like, again, two straight lines that intersect precisely at a certain point. That's the point number one. So let's say we will call this point, I don't know, we'll call it O. That's one common point. And what's the second point? That's right, the second point is the point at infinity, and that is the structure of the, again, don't forget, primitive hyperbolic pencil of circles. And it turns out that there exists a theorem according to which for every primitive pencil of circles, elliptic, parabolic, and hyperbolic, there exists a corresponding inversion of the parent plane, inversion of the parent plane, inversion of the parent plane that will take the corresponding primitive pencil of circles into non-primitive pencil of circles, non-primitive and non-primitive. And the structure of these non-primitive pencils of circles is the following. For the non-primitive elliptic pencil of circles, we have the set of all circles that pass through two fixed points. I try to show them in red, but this point and this point, these circles genuinely intersect, and the non-primitive elliptic pencil of circles also contains this vertical straight line I showed over here. This is called the radical axis of this pencil of circles. This is a straight line that passes precisely through these two fixed points. The structure of the non-primitive parabolic pencil of circles is the following. This is the set of all circles that are tangent at a particular point. And this pencil of circles also will include this vertical line right here that passes through this point, and this straight line will also be called the radical axis of this pencil of circles. Lastly, the structure of the hyperbolic pencil of circles is the following. These are the circles that are, in a sense, contained one inside the other, two sets shown here and here. They have no points in common, but eventually they converge into a point, and this pencil of circles, in addition to the genuine circle, contains this straight line over here. It's also called the radical axis of, let's say, this time, hyperbolic pencil of circles, and you will drill deeper and deeper. You will prove all these theorems in this course, or when you start studying the theory of the pencils of circles, and you will also come across the following idea. I will symbolize it over here. It turns out that it can be shown as, again, a theorem, let's say one theorem, that each and every pencil of circles of specific type has precisely one, and exactly only one pencil of circles that is orthogonal to the given one. And the relationship between these orthogonal pencils of circles is the following. Let's say we have an elliptic pencil of circles. Then to an elliptic pencil of circles, an orthogonal pencil will be hyperbolic pencil of circles, and conversely, a pencil of circles that is orthogonal to a hyperbolic pencil of circles is an elliptic pencil of circles, and that leaves us with the parabolic pencil of circles. And the deal here is the following. The pencil of circles that is orthogonal to a given parabolic pencil of circles is still a parabolic pencil of circles. Another flavor in which you can increase the width of your knowledge of inversive geometry is to take the information that you already possess and embed it into a new environment. In other words, you can study the inversion of the complex plane this time, not the real plane, but the complex plane. And here, conceptually, there will be nothing new. You will still have the same workhorse algebraic idea that underpins the inversion of the plane in a circle, but you will have the new context in which you will study the same notion or the same idea. Here you will have the real axis, the imaginary axis. You will have real numbers on one side, you have all imaginary numbers, purely imaginary numbers on the other axis, all the beautiful stuff that the complex plane provides. And here we will place the same circle, lowercase s, with the center located at the point uppercase S. The radius of that circle will still be r. This is the radius, and if we grab any point z located somewhere, let's say outside of the circle S, then its inversive images will be a point we already know that will sit inside of the circle of inversion. We'll call this point z prime, uppercase for the name of the geometric object, lowercase for the corresponding algebraic object, the complex number. Technically and pedantically, numbers are numbers, points are points, and points are not numbers, numbers are not points. There is a bijection between numbers and points and so on, but leaving all these gory details aside, the fundamental idea when you will be studying the inversion of the complex plane will still be the same. The product of these two distances from the center to the point, and from the center of inversion to the image of this point is the square of the radius. But the thing is, the algebraic apparatus over the set of complex numbers is a little bit different. Here, the distance between 2 points, S and Z, is a square root, and we do not want to deal with square roots. So the first maneuver that we will do is we will square this workhorse algebraic relation. Here we will have the fourth power of the radius squares of these guys, but for any complex number, we know that this is the case. And this is another idea which we take from here into here. We rewrite these distances as so. Then we take this distance, flip it into this expression like this, see? Like this and like this, based on this. But then what we do is we keep these two factors. This factor times this one will be another r squared. This is another exercise. You will show it by yourself. Open up the parentheses and see what happens. But this time we will leave that just this expression, and we will cancel one copy of the square of the radius. But this time we will take it with the sign plus minus. What is the plus? The plus is for the positive power of inversion. And what's the minus? Minus corresponds to negative power inversion. The same the same notions that you learned in our course as it pertains to the real plane. Now, when you will solve this equation for this here variable, maybe even let me highlight it for you in red, you will solve this middle school equation for this variable z prime. Then you will have two expressions depending on the sign in front of the square of the radius of inversion, which corresponds to the power for the positive power inversion, positive power of inversion, so plus r squared. You will have this relation over here, which captures the location of the image of the input point z in the complex plane under the inversion of that plane in a circle that has its center at the point S and the radius r. So here S conjugate, don't forget conjugate, conjugate. For the negative power of inversion, when we take negative r squared, then here already it becomes quite pleasant because we can always capture the minus r squared as this formation shown over here. So in some sense, we can say that the radius of the circle in this case becomes imaginary. So I r squared becomes a minus, so this minus sits over here, this guy right here. So for negative power inversion, this is the algebraic manifestation or an algebraic essence of what does it mean to reflect this point z in a given circle that is located, that has its center at S, radius r. Still we have conjugate conjugate plus S. This is the expression, don't forget the minus, or if you do not like the minus, you can move it under the square, but then you'll have to say IR, the whole thing squared. This is the denominator plus S, and once you start working further and further, you will see that in this particular vocabulary, you will not see your favorite algebraic representation of the complex number z as x plus I times y. You will not see that. But instead, what you will see is that the arithmetic of the genuine complex number and its conjugate image will be your dictionary, if you will. This is what you will do, the arithmetic of complex numbers and their conjugates. You will never see here x and y, only z and its conjugate images as shown over here and over here. And again, once you start working more with this, you will come to the so-called linear fractional transformation of the first kind. This is a favorite, this is the famous Möbius transformation. This is the first kind, and the transformation of the second kind, well, let's call it G of Z, is basically the same thing, but instead of the original, we take the original variable Z, we take its conjugate image Z with a over line right here, and again, you see how naturally these things emerge. That's how mathematics develops in general. We take the existing notion, embed it into a new space, do a little bit of algebra, and all sorts of wonderful things pop out. Yet another flavor of increasing the width of your knowledge of inversive geometry is to get introduced to inversion of the real plane or even the complex plane, if you did the complex plane before, in conic sections, and that will be an ellipse, a hyperbola, and a parabola. So let's say how we would define the inversion of the real plane, let's say in an ellipse. Well, if lowercase e is an ellipse and we have its center, let us pretend that this is my artistic rendering of such an ellipse. Let's say we're given a point A that is located outside of an ellipse, and then how do we construct the image of that point A prime? Well, the technology is similar, but again, this is we'll have to learn a new concept, or a polar of a point with respect to a quadratic curve, in this case with respect to an ellipse. Well, when the point A is located outside of an ellipse, the way the polar of that point with respect to that ellipse is constructed as follows. You draw one tangent to the ellipse through the point. You draw the other tangent to the ellipse through the point, and you'll obtain 2 points of tangency. And in general, they will be skewed somehow in a funny way. Well, these 2 points will define a unique straight line that will be a polar of this point with respect to this quadratic curve called an ellipse. We draw that polar, and where the polar intersects the straight line that connects the center of this curve with the given point precisely marks the spot. This is our image of the point A under the inversion of the parent plane with respect to an ellipse. And the workhorse relationship is the same. The product of the distances OA to OA plus is equal to the OD squared, OD this time. This will be somewhat new notion. It will be a diameter of the curve, so this time OD will be defined like so. When we connect the given point with the center, that straight line will intersect the ellipse. Well, technically at 2 points again, but you already understand. So if we want to flip this point on the other side, we will do a similar thing, but the diameter will be here, and the point A prime will be located in such a way that the center of inversion will be in between. But that's already minute details. You do not need to worry about this. Conceptually, this is how the inversive images of the given points are obtained when you begin studying the inversion of the plane in the conic sections. It's intersection of the polar of that point with respect to the given curve or the given section and a diameter of that curve. And now we can look at how the inversion of the plane can be defined in terms of a parabola. If we're given a parabola P, then let's say we're given a point that is located with respect to this parabola this way. So what we do here is this: in the parabola this time we don't have the so-called center that an ellipse has or a hyperbola has, but we have its axis of symmetry. So what we do over here is we construct a straight line through the given point that is parallel to this axis. Now it goes like this. Let's see if I can do it. Let's see, this way. And then Apollonius of Perga, let's say about 2,000 years ago, actually proved that if we reflect this point like this into point A prime, such that the distance AD is equal to the distance AD prime, then we just inverted the plane in the parabola. Consequently, we understand how to construct the image of a given point if it's located, let's say, inside of a parabola like this. You see, we construct a straight line parallel to its axis where it intersects the parabola. We'll mark this point as D, let's say, and then what Apollonius proved is that this distance A prime D is equal to the distance AD. And lastly, let's say we're given a hyperbola that is shown over here. It has a nice center. We call it center O. And we're given some point A, and we want to invert or reflect this point in such a hyperbola. What will we do? Same thing we did with the ellipse. Through this point, we will construct 2 tangents, let's say this way and let's say this way. These 2 tangents will define a unique straight line. That straight line will be called again the polar of the point A with respect to this hyperbola. And by the way, once we have that straight line, let's say we have it, a polar, then the point with respect to that straight line is called the pole. So this will be the pole, P-O-L-E. This is the pole of that straight line. So once we have two tangents, they define 2 points on the parabola, on the hyperbola, I'm sorry. So these 2 points we snap a straight line. This is called the polar of this point with respect to this curve. And what happens? Well, this polar will intersect this straight line right here, like this way, and this will be the image. A prime, again, will have the same point D over here, and the same relation over here exists. The distance OA times OA prime is OD squared. Again, don't forget that the straight line through the given point and the center of the hyperbola, this y, intersects the polar. You see the polar. That's how we construct the images. Intersection of the polar and a diameter with the given curve. And lastly, you can bravely step into 3 space and leave the confines of the plane. And here you have a number of interesting surfaces of revolution, first of all, to study. And the very first one that you really should take on or try to take on is a sphere. Here you will have a lot of fun trying to extend or convert some of the theorems that we proved in this course already into the 3-space environment. And let us think together about the following fun question together. You already know that if this is a circle of inversion C, this is the center of inversion, and this is a straight line L that touches the circle of inversion at a given point, let's say T. The inversion of the parent plane with respect to this circle will crumble this straight line into what? It will crumble it into a circle that is tangent to the circle of inversion at the point where these two objects are in common, the point in common between these two objects, and that passes through the center of inversion. By analogy, if we were to prove a similar theorem, let's say this is a model of a sphere, this is a model of a plane, we have a plane that touches our sphere. What will this plane be taken into by the inversion of the space in the given sphere? Well, it should be evident that such a plane will be crumbled into a sphere that touches the sphere of inversion internally and passes through the center of the sphere or through the center of inversion. And in some sense, if you go all the way back to my introductory episode, the very first episode of this course, you will see that this is precisely what we started with the inversion of the 3-space in a sphere. But as far as I'm aware, it is also possible to give a meaningful definition of inversion of the 3-space in the ellipsoid. And in some sense, increasing the depth of our menu of exotic surfaces with respect to which it is possible to define a meaningful inversion of the space. It is possible to invert the 3-space in the so-called paraboloid of revolution. And such a paraboloid has the following interesting property. If we intersect such a paraboloid, let's say this is the z-axis, this is our x-axis, this is our y-axis. If we intersect or cut such a paraboloid with the plane anywhere over here in this area, like so, then what will result? In the plane that is perpendicular to the positive branch of the z-axis over here in 3-space, given the traditional orthogonal coordinate system. Well, the intersection of such a paraboloid of revolution and the plane will be precisely a circle, because there are other paraboloids possible where the such intersection of the plane perpendicular to the z-axis, to the positive branch, will produce not a circle but an ellipse. Evidently, then this will not be a paraboloid of revolution, and as far as I'm aware, it's perhaps possible to invert the space in the so-called elliptic paraboloid as well. But in addition to this, it is possible to come up with a meaningful definition of inversion of the space in the hyperboloid of one sheet and the hyperboloid of two sheets. And if you study the inversion of the space in these interesting or popular surfaces, you may be able to come up with a way to invert the 3 space in some interesting surface. Now, this is it for this course, and I wish you the best of luck in your further study of inversive geometry.